It's my great pleasure to have Leo Radzihovsky here today for our colloquium. So Leo did his undergrad and PhD at Harvard, and he did his PhD with David Nelson, where he was working on classical statistical mechanics problems, I believe. Actually, I'm not sure I know the topic of your thesis, but and then you went to Chicago he went to Chicago as a postdoc, and then in 1995 became a professor at Boulder, where he has been since, although he has had many visiting positions and is, I think, a sort of very collegial figure in the field and works with lots of people. And so he's won just about every award you could imagine, the Sloan and Career and Packard. He's an APS fellow. He was a Miller professor. He's a Simons investigator and many other awards. He's well known as an organizer of the yearly Boulder Summer School, which for students of condensed matter is something of a key destination that they try to go to, both for the physics and to enjoy Boulder. And so one of the things that really sticks out to Leo is about Leo to me is sort of his diverse interest in physics. And so I first encountered his work in the field of ultra-cold gases, where he was looking at attractive fermions, as many people study here, and also attractive Bose gases, and had some beautiful predictions about a phase transition in ultra-cold Bose gases that may finally, 20 years later or something, be on the cusp of being observed or have been observed. And so his work on ultra-cold Fermi gases has been really foundational to the field. But he's I wouldn't call him an ultra cold gas person. He's very diverse, and so he has published many papers in soft matter and studied tubules of something, whatever those are, and he's looked at lots of liquid crystals, and he's also worked on hard condensed matter problems like semimetals and disordered semimetals. So I think it's, we can all aspire to have such a broad view of physics as Leo does. Today we're going to hear about something that is maybe in some sense a crossover between some of these fields, fractons, which are of great excitement to the quantum condensed matter community and also quantum information community, and what that has to do with elasticity, which is maybe more of a soft matter community. So anyways, I'm excited to hear what he has to tell us. Leo, whenever you're ready.
Okay, Caden, thanks for that really generous introduction. I appreciate it. It's nice to be at Rice, even if not physically, in spirit. I don't think I've ever visited, so that's a hint for you guys to invite me back so I can come and have some coffee with you and maybe dinner and a beer. Yeah, so I mean, to answer Caden's question, I was, when I was a grad student, I worked on membranes, actually fluctuating extended objects, and so that was. And at that time, it was actually, the focus was on, well, physical realizations were phospholipid bilayers or some biological membranes. People were doing light scattering off of cytoskeleton membranes of a red blood cell that they would extract from red blood cell. And so the theme of my sort of development was sort of studying stat mech and field theory of extended objects, from membranes to polymers to like vortices to charge density waves. But then, I went to Chicago, where there was, although a lot of soft matter, but I was hired to do, work with Paul Wigman to do hard condensed matter physics and solve the mysteries of ITC superconductors. And I utterly failed, but somehow I still landed in a good job in Boulder. So I was very lucky. And of course, once you're in Boulder, there are two kind of key groups in Boulder. One is soft matter and liquid crystals, and the other is of course AMO group. And so of course I couldn't help but be influenced and moved in that direction. And it's been so. I'm a dabbler in many things, and maybe master of none. But it's still, I have fun doing it. So this talk is as Caden alluded to, is maybe quintessential cross between my hard matter quantum interest and soft matter, and maybe is an illustration where if you pay enough attention to soft matter, you may actually make a little bit of contribution in the hard matter. So I'm going to share that with you, but it's a colloquium, so I'm going to start out slow, and there's a lot of intimidating, maybe I have heard words in my abstract and unknown words like fracton in the title, so I hope to demystify those. That's really the point of this colloquium. So what I'm going to tell you about is a pretty exotic, pretty eccentric corner of already very exotic field of quantum liquids. And that corner is the Fractal corner of the quantum liquids. It's the new class of theoretical models. And I'm looking at Randy, and I compelled to apologize, and looking at other experiments like Tom, to apologize that there will not be much experimental content in this talk, unfortunately. So that's a failure of this field. But on the other hand, that's what happens when you try to hopefully break theoretical frontier, and then, convince experimentalists, good experimentalists, that you're not crazy, and maybe they can follow up. So anyway, I'm going to tell you about a corner of this quantum liquid field, of a new class of quantum liquids that are so far only appear in theoretical models, called fractons. And so that's pretty esoteric, but what's kind of the main message of the talk will be, and that's my little contribution to it, is that this seemingly exotic field of fractons is connected to 200-year-old subject of elasticity of crystals and topological defects. So that's kind of exciting, because it's, in some sense, at least for some fracton systems, this allows us to demystify the subject at least a little bit. And so my goal will be to explain these two corners, and then use duality to show you how these are related. And the field is really growing very quickly, so I won't be able to cover all of it, but I'll give you kind of some bird's eye view of it. But the subject that I'm going to focus on, and where I've contributed, is here are some of the papers that have appeared on the subject of this relation. And the primary person is this talented postdoc is Michael Pretko, who we started this journey with. But then I worked with a very talented student, Zai, who is now moving on to a postdoc, and also collaborated with Michael Hermele, my colleague in Boulder, more recently. So, because this is a colloquium, let me start off from the beginning and try to put this in a broader context of condensed matter physics, where, the subject is to try to understand phases of matter, those we see around us, and maybe those that are hidden inside a crystal or inside, are more subtle, and you can't as easily distinguish as you do, very simplest states of matter. And so while, the pictures that we learn in high school or maybe even middle school of condensed matter is quite bland, as illustrated by this phase diagram, in reality, we all know, the condensed matter to condensed matter physicists, and, really to everybody, should really look like illustrated on this slide. And in fact, not maybe, this is a gross oversimplification and only a cross-section of the kind of things that we're interested in. And in fact, there's a little corner here that's left that I reserved for Randy. There's a BC appearing here that's growing at low temperature. So, in fact, the field has there's a lot of cross-disciplinary relations to, quantum field theory and particle physics, quark gluon plasma, on one hand, but on the other hand, to fields like AMO, where there's traditionally has been a distinct field, but now there's the synergy between various fields of physics. So it actually broadens significantly the scope that's illustrated on this slide. So one might ask, what is so unifying about, examples that appear on the slide? Why are they all fall under, what's the common theme that makes them fall under the same subject? And of course, there's really two ingredients that really unify these. And that is strong interactions, which means that's the word condensed. Things are condensed, meaning they're packed together unlike a gas. And the second ingredient is that there's a macroscopic number of degrees of freedom. So those are really the two ingredients that lead to this amazing richness that we see around us. So, N is much bigger than 1, and, strong interactions, U is much bigger than 1, where U is some measure of interactions. And so so that's the richness, and it's summarized by this famous adage from Phil Anderson, more is different. And so, given this complexity and given this parameter regime that we want to look in, one might wonder whether we can ever make any progress. But on the other hand, amazingly, this regime also, this more is different, also is also the simplifying feature. It turns out when you go to a large number of constituents regime, then sort of emergent universal laws end up controlling the physics of the system, and so we don't have to work as hard. We need to try to understand what these emergent laws are, but we don't need to spend so much time understanding the microscopics and deriving things from the very microscopic description of our systems. And here I gave a slew of familiar examples that come under the scope of condensed matter physics, where new emergent phenomena appear, and they only appear when you go to this macroscopic thermodynamic limit. And you can read it. You can read the examples, and they're certainly very familiar, from fluids, hydrodynamics of Navier-Stokes equation, where waves and shear flow and viscosity appear, to elasticity of crystals and generalized elasticity of superfluids and liquid crystals and rubber, and even things like long scale physics. Einstein gravity is sort of the simplest thing that can appear at long wavelength physics. And of course, quintessential examples, of course, critical phenomena and vicinity of a critical point controlling a continuous phase transition between two phases. Okay, so again, how do we take advantage of this universality and this kind of emergent phenomena to actually make progress? Well, there's one, at least a half, but I would say much more set of phenomena, and that is, I call bosonic matter. So this is conventional bosonic matter that obeys so-called Landau paradigm and allows us to completely understand, although there's a lot of research, of course, is still going on in this subject, at least at the very fundamental theoretical level, we understand all the ingredients to be able to classify and characterize states of bosonic matter that obey this Landau paradigm. And so this is what I call conventional ordered states. These are the interferomagnets, superfluid, liquid crystals, you name them. And so what Landau has taught us is that there's a local order parameter, and that local order parameter distinguishes a disordered phase from an ordered phase, or one ordered phase from another ordered phase. And really, the characterization of phases, classification of phases, is really done by, phases are characterized by different patterns of spontaneous symmetry breaking. So, distinguishing, let's say, a crystal that breaks translational symmetry in a certain way from another crystal that breaks translational symmetry yet another way. It has a different space group symmetry. And both of those are distinct from a liquid that has continuous translational symmetry. And so here, just sort of schematically, I illustrated a ferromagnet or a pneumatic liquid crystal as the ordered phase of a paramagnet or isotropic phase. And you can see, you can image, for example, for liquid crystal, you can image this order parameter when you go to a pneumatic phase and you look between cross polarizers, you see these beautiful textures between cross polarizers, and this is your order parameter fluctuating. If it was not fluctuating, or if it was completely disordered, you would see this black pattern. And so you indeed, this is a local order characterization of the distinction between these two phases. And so although I would say, 99.9% of the states of matter that we know and are accessible to us, and certainly the ones that have been experimentally realized, fall under this Landau paradigm. Although I should say there's a second half of those are the fermionic systems. They also fall under Landau paradigm, but different Landau paradigm, those of the Landau Fermi liquid theories. But let me focus on bosonic matter. Although most of the matter that we know, and certainly the ones that have been experimentally demonstrated, are fall under this Landau paradigm, much of the field, so the theoretical field, has moved, for the past 30, even 40 years, dating back to, well, actually going back to high TCs maybe as the primary motivation, try to understand anomalies in the high temperature superconductors, but many more since then, where one encounters phenomena in solid state physics or condensed matter physics, which somehow violates this standard Landau paradigm. And, the quintessential examples, very famous examples, are the quantum Hall states that are often cited. But then, there are many others like frustrated magnets, and maybe that's about it. There's all kinds of materials that I'm not actually very much familiar with as a material scientist, but there's a number of systems that seem to display at least intermediate range of temperatures where there's something where the system fails to order, but nevertheless has pretty exotic, it has some non-trivial underlying but non-local order. And, again, maybe best example is a quantum Hall effect where, if you take two quantum Hall fluids at two different filling fractions, two quantum Hall plateaus, locally they look identical. It's just a liquid of electrons in the magnetic field. On the other hand, if you measure Hall conductivity, those are quantized, and they're quantized to a different Hall number, a different Hall conductivity, different number on the lattice characterized by a Chern number. And so we know those fluids are distinct, but nevertheless, they're not. There's no order parameter that you can write down to capture to distinguish them. And so much of the field has focused on these, what I call quantum liquids, but to distinguish them from the main subject of the talk, I'm going to call them conventional quantum liquids. And there's a particularly simple model, a toric code model due to Kitaev, that here's a Hamiltonian that illustrates this, that if you're familiar with it, that one can it's exactly solvable, and one can keep in the back of his mind as an example. But all these systems have the following common properties. They have non-local excitations, bulk excitations, that are fractionalized, meaning they are anionic. They are not conventional fermions or conventional bosons, or they have some fractionalization. Namely, the actual excitations are not simple composites of finite composites of the elementary degrees of freedom, like bosons or fermions or spins. And these excitations appear at the ends of strings typically. And so here's a cartoon that comes from the toric code model, where you can have excitations where you create when you try to create an excitation by flipping spins on these bonds. So think of spin 1/2 model, where you flipped all these bonds, spins on these bonds. And what happens is then you get excitations that appear. You can think of them as electric charge excitations that appear at the end of the string. The string is like the electric field line that can still fluctuate. And so really this is like the discrete version of electrodynamics, where you have electric charges connected by electric field lines. You can also have magnetic charges where you violate a plaquette, and that would be like a magnetic analog of a magnetic monopole, but in this discrete two-dimensional system where there's a magnetic field line connecting it, which is the violation of these red bonds here. So these are the E and M particles that appear in the toric code, and is an example of these anionic like non-trivial excitations that appear at the end of the string. But what's important is these excitations can actually move around without any problem. They can hop around, and what that does is it just requires a string to get a little longer or a little shorter. Okay, so they're not constrained. There's a statistical interaction between them, but they can hop around with no restricted mobility. They also exhibit these theories exhibit topological order when you consider them with periodic boundary conditions. But that topological order is usually of order 1, so it may have a degeneracy of 2 or 4, some kind of a simple small number degeneracy. It's not an extensive degeneracy. In the modern parlance, we say they're long-range entangled, which means these states in no sense are very far from a product state that one might write down for a trivial state. And most importantly, they're described by gauge theories, various kinds of gauge theories. Here's a cartoon of it. You start out with some kind of a microscopic model of spins on the lattice, but then for particular models or particular geometries, what emerges at low energies, at long wavelength, is some kind of electromagnetism, which is not real electromagnetism, but it's a way to encode low energy degrees of freedom, quantum degrees of freedom of this spin model. So it's kind of cool that electromagnetism just emerges from microscopics. And this has been the belief that all quantum liquids up until the subject that I'm going to talk about emerged, these conventional quantum liquids, they're all one way or the other are characterized by these gauge theories. But what I'm going to tell you about a class of systems that are not characterized by these conventional gauge theories and are, where, these characterizations that I described that are qualitatively different. So we call those fractonic models. So these are the new type of quantum liquids. There are many, there's a kind of an explosion of models that exhibit fractons, which are excitations of these models. And maybe to let the cat out of the bag, fractons, if you learn anything from this talk, even just to know what the term is, it's an excitation of these models, which cannot move. You can create it anywhere, but once you create it, unlike anything else in quantum mechanics, even if it's a model is generic, it just has zero matrix elements to hop around, even though the system is translation invariant. So that's kind of an incredible thing. And so I will discuss that in more detail, of course. So there's a proliferation of models that exhibit this kind of a fracton behavior of these fracton quantum liquids. And among that class of models, there's one class, which are gapless fractons. I mean, you could say it's half of those, half of the fractons are gapless fractons and they're gap fractons. So I'm going to talk about gapless fractons, and those are described by some new kinds of class of gauge theories, the tensor gauge theories. So I'm going to explain what those tensor gauge theories are. You don't need to know anything about them except to have taken a course on the E&M. And then I'm going to talk about something completely seemingly orthogonal, elasticity in a crystal. So that's going to be another direction. And then what I'm going to do is I'm going to tie these together using a concept of duality. So this is going to be really the punchline. If I get to here, everything will be great. And then everything else is kind of icing on the cake. Okay. So let's start out with this Fractal Matter, these new kind of quantum liquids. Again, just a disclaimer. I'm not talking about anything physical or realistic or at this point. There's no even kind of well, some people might claim that they have some potential realizations or potential, but they're certainly not explored experimentally in any concrete system. These are now just models, okay? And what I'm going to introduce it just because for historical reasons, that's what people have been studying and first discovered it. In fact, the original paper goes back to Claudio Cimon in 2005, but he didn't know these were fractons. And there was sort of a renaissance with Jianwen Ha in 2013 and many others that followed, all these and ... There's been an explosion of studying and coming up with these models. These are gap models, which is why I call them Z2s. They're made up of spin 1/2, so they can be either +1 or -1 or 0 and 1. And in fact, the motivation of Ha's motivation was to construct Hamiltonians for robust quantum memory. So he was thinking of this really from the quantum information perspective. And so to him, these Hamiltonians were really codes, like quantum codes as in a quantum computer, as a way to either do quantum computing, but maybe as a first step to encode information and namely make a robust quantum memory, okay? So I don't want, because this is not central to my subject, to what I'm really gonna talk about, I don't wanna give detailed Hamiltonians that describe this, except maybe to say a couple of words about sort of at least schematically what happens in these models. So typical Hamiltonian consists of terms, a sum of bunch of terms, and each of these terms can commute. Each of these terms commute typically, And so because of that, you can solve these models exactly. You can diagonalize each of these terms because they commute independently. So let's focus on one of these terms. So what is one of these terms? So in the simplest model called the X cube model, imagine a cubic lattice in 3 dimensions, and in every bond, you have a spin 1/2 degree of freedom. So it could be either 0, up or down. And the energy of this term, A, this component of the Hamiltonian, would prefer that every cube has a product of spins. Here's the product of spins. Think of them as sigma z's, that their product is +1. So that's that's what you want. And that's the ground state is all these are +1. So of course, there's these other terms that commute with A, but nevertheless, there's sigma x terms which can flip these spins. But let's just focus on this one term. And so imagine all my cubes in my cubic lattice have +1, which means these spins, the product of these 12 spins is +1. But imagine now I go and I flip this bond right here with acting with a sigma x. So what happens? Well, now this bond is shared by 4 cubes. Okay, so in fact, let me maybe draw it here. So imagine I flip just this one red bond. So then,
Leo, if you're drawing something, I'm missing it.
Oh,
Again,
I'm sorry.
please.
So let me, well, okay, you can imagine, can you see this?
Yep, we can see that.
Yeah, so here's another cube, and then there's a cube above it, and there's another cube here. Oops, here. Sorry for the bad picture. So there are 4 cubes that are sharing this. So think of those cubes, because now they have -1 on one of the bonds, they're violated. They have a cube that has -1, and that this term A has become -1 for those cubes. Imagine now I flip one more bond. So let me now erase this. Imagine I flip one more bond here, the second red bond. Here it is. So I flipped one. So then there was 4 cubes. Here they are. But then I flip another bond. Now the cube has moved out. This cube stayed, but this cube violated one, moved out. Why is the one in between not violated? Because it has 2 red bonds that have been flipped. So the product of those has still +1. So this is just to motivate, to show you that what you can do is you can create excitations, but they appear as a quartet at the corners of this rectilinear membrane. And they cannot individually, if you really go through this dynamics, each of them cannot move independently. They can only move by making this longer or broader. But, so the pair can move, for example, into here, but individual cube cannot move. So these cubes are the excitations, these violated cubes are the excitations, and these are the fractons. Okay, so that should give you some intuition. And there, so that's an example of a fracton model. So again, so the key thing is these fractons appear at corners of extended objects. And I want to contrast it with what I talked about before. I had electric charges appearing at the ends of the string, rather than fractons appearing at the corners of a membrane. And so for a string, I could just grow a string. But a membrane is not so easy to grow. I can't do this. I can't move this. I can't move this one fracton. So fractons are immobile. If I insist on moving one fracton, so let's say I have this fracton, I can create it anyway. If I want to move it here, I have to create 3 other fractons at the corners of this membrane. Okay, and that will be off resonance. That's a process that will cost energy, creation of these extra particles, 2 extra particles, and so it will not happen unless you give some energy. And so this is the sense in which this thing is immobile. There are other excitations in these models. Typically, there are some kind of a dipoles, and those there are planar excitations, which only if the dipole is like this, they only move in the plane perpendicular to the dipole. Or some of them, if the dipole is like this, they move only along the dipole. They're not allowed to turn.
So these Leo, can I ask a question?
Yeah, so let me just, these are called planons, these are called line-ons, and these are called fractons. Yeah.
So I think implicit in your discussion is the idea that these extended objects can't really change their shape. So if it's a square, I can stretch the square, but I can't really sort of pull on one corner to make it a trapezoid or something,
That's
because
right.
then I could move one fracton. So I know in the X cube model, that's certainly the case, that you can't sort of bend these things. Is that the case in all fracton models then?
Yeah, so yes, that's the case. And that's because we consider specific lattice. The lattice is not dynamical. There are no phonons there. So in principle, one can try to think about maybe coupling these models, consider these models now on a fluctuating geometry or something like this, where then there's a potential for something new. But and these models are very strongly lattice dependent, which is why we say they're beyond quantum field theory, in particular topological quantum field theory. And also I failed to say that these models have ground states that have exponential topological degeneracy. They don't just have degeneracy like the toric code, which is of order 1. They really have exponential degeneracy that's exponential in the system size. So, so that's kind of exciting. It's very difficult to come up with models like this, although now there's an explosion of these kind of models. But as you notice, for example, this speaks to the point that I made that there's no experimental realizations. This one term, let's say the A term, involves product of 12 spins. So it's not even a 2-spin, it's not 4-spin, it's not 8, it's 12-spin models. So, and there's many more, even more complicated models. And so that's challenging to try to tell experimentalists, make a model where 12 spins interact, right? So it's kind of hopeless. So anyway, so with that kind of a one sort of a introduction to what these models look like, I'll just do injustice to all the other models and all the other sort of approaches to just say that, and this is highly outdated slide, that there's huge number of approaches to producing these models and studying these models, and it can get really extremely mathematical beyond my sort of comprehension. Sometimes you can take lower dimensional models and string them together in a certain way to make a 3-dimensional model, couple them in a certain way to make fractonic models. But this is going to be irrelevant to me. I'm going to focus on a specific realization called gapless fractons, which are realized in the higher rank tensor gauge theory, which I'll explain next. So what are tensor gauge theories? Well, just recall your electrodynamics, conventional electrodynamics, maybe quantum version of it. So first classical version, you have a Hamiltonian. What is the Hamiltonian for electrodynamics? Conventional electrodynamics is just E squared plus B squared. But now if you want to make it quantum, so quantum electrodynamics, you just have E and B, and E and B are canonically conjugate. So you can think of this is the Hamiltonian formulation of quantum electrodynamics. You can think of this as like P, and this is Q. This is like P squared, and this is Q squared. And this is the canonical commutation relation between P and Q. So then it really is just a bunch of harmonic oscillators on the lattice. The difference is that, the actual degrees of freedom, although you formulate in terms of gauge degrees of freedom, the vector potentials, the actual, what actually appears are curls or gauge invariant quantities. And that this Hamiltonian commutes with the Gauss's law, and the usual Gauss's law is divergence of E equals to rho. Okay, and then B is derived from A as some kind of a curl. So what a tensor gauge theory is, what tensor gauge theory is really exact, similarly, just a generalization of what I just described, what's familiar to you from electrodynamics, except now E and A are symmetric tensors. And here I took it to be 2-index object, rank 2, but you can generalize it to higher rank objects. And it's not, and again, there are many different versions of this theory, but one version of it is called the scalar charge tensor gauge theory, where the Gauss's law is very natural, has a double divergence. The usual Gauss's law is if your electric field is a vector, the usual Gauss's law is just a single divergence on that index I that gives you the charge density. But here I have 2 indices, so it's very natural if this is going to be a scalar to contract both indices. So I call it double divergence Gauss's law. of scalar charge theory. So you might say, what is that? And why do you want to do this? And what does this have to do with fractons? What incredible, as was first pointed out by Michael Pretko, when he was still a graduate student at MIT, so it's kind of an incredible creativity insight. These tensor gauge theories, he didn't invent them, people have been studying them, but he was the first one, to my knowledge, to point out that they exhibit fractons. And so let me just try to make that very intuitive. It all comes down to this. So usually when you have an ordinary Gauss's law, what we have is a conservation of charge. Why do we have conservation of charge? Because I can integrate both sides of this equation, and then the total charge in the big volume just becomes a boundary term. So the charge cannot change locally. It can only come in from the boundaries. It can flow in through the current via current through the boundaries. But that's because you have a single divergence. But here you have double divergence. So here you have charges that are conserved, but you also have dipoles that are conserved. So if I think of a dipole, charged dipole, namely xi rho, that's the dipole density, this object will also be conserved. And that's because I can replace rho by a double derivative of Eij, and then integrate by parts twice. And I can kill this xi and make a boundary term. And so as a result, dipoles are conserved. But and that immediately leads to Fracton phenomenology. Why? Well, very simple. It's just the observation that a motion of a charge, here's a charge, and I want to move it, can be thought of as just creation of a dipole. If I move a charge, I add a minus charge here and I add a plus charge here. So I'm creating a dipole. But I'm not allowed to create dipoles because dipoles are conserved. So if I were to do this, if a particle were to hop, I need to add an opposite dipole plus minus to compensate minus plus dipole. Well, I don't have enough energy. If I'm, on resonance or, on shell, there's no, if I'm not inputting any energy, I won't be able to, there's no energy to do that. And because of that, this particle cannot move unless I provide the energy. And so this charge from this tensor gauge theory is immobile because dipoles are conserved, as is explained here. Okay. On the other hand, depending on details of the theory, you could look at vector charge theories or scalar charge theories and a few other ingredients I don't want to get into. The dipoles themselves can move, but often they move in a weird way where, for example, they can only move perpendicular to the dipole, but they cannot move along the dipole, for example. So these, you would call these particles have a restricted mobility. So, so then naturally one is thinking, are there any physical realizations? And this is sort of where maybe I entered the subject in 2016, where I realized that this phenomenology is actually reminding me of something that I've studied over the years, and that's namely topological defects in the crystal. But in particular, I'm going to focus on a two-dimensional crystal. So I made this conjecture after checking various, making various checks that phenomenology kind of agrees. The phenomenology we know about fractons seems to be reflected in the phenomenology of topological defects in the crystal, but there was no proof of it. There was just this conjecture in 2016. But then, I began to collaborate with Michael Pretko, as I will describe, and we were actually able to show that the two theories are actually related. But before I do that, let me tell you about topological defects in the crystal. So sort of taking a 90-degree turn and telling you about something completely seemingly unrelated, namely defects in the crystal. And again, I want to focus on two-dimensional crystals. So two-dimensional crystals, of course, have phonons, and those we'll discuss. But in addition, they have topological defects. The elementary topological defects is a disclination. Here's a seven-fold disclination where all the atoms in this triangular lattice have a six-fold coordination. But this one atom, I've added an extra wedge, 2π/6 wedge, here, this wedge, out to infinity. And as a result, this guy has this point or this lattice side has 7 coordination. Here it is 1, 2, 3, 4, 5, 6, 7. On the other hand, I could cut out a wedge out of a triangular lattice, and now I have a 5-fold coordinated side. So this is like a plus, minus 1, minus 5 and 5 and 7, or minus 1 and plus 1 disclination. There are also dislocations, which are dipoles of these disclinations. If you put this plus and minus together, you can create a dipole. And there's something very special about these dipoles, which are called dislocations. They move in a funny way. That's known, was well known, probably for more than half a century, going to the, sort of founding of the field. Namely, these dislocations, they have hard time what's called climbing. So if you have a dislocation here, the dislocation is characterized, you can think of a dislocation as an extra row of atoms that ends here, and it's characterized by a vector which is perpendicular to this row of atoms. So it's a Burgers vector. It's called the Burgers vector. And you can see here that this dislocation has hard time moving in the direction perpendicular to the Burgers vector, because if it moves this way, it has to get rid of this atom. So this atom has to go somewhere. So if you don't lose atoms, if you don't have any vacancy interstitials, that's what I call V/I, then you can't get rid of this atom. And so then this dislocation cannot move this way. It can only glide, as we call it. It can move only along the Burgers vector, but not perpendicular to it. So this is the glide mode, and this is the, so for example, if you do have vacancy interstitials in your crystals, you inadvertently do it, always do at finite temperature, then diffusion of dislocations, the climb is far smaller and vanishingly small at lowering temperature than the glide illustrated here. Okay, so if that's true, then maybe one would predict that disclinations cannot move. Well, sorry, so if I identify these defects, namely disclinations with fractons and these dislocations with dipoles of Fracton and Gage theory, as I originally did, then one should be able to understand completely on the elasticity side why a disclination cannot move. So here's a cartoon sort of illustration of this. So imagine I cut out a wedge out of this, out of my crystal. So here's the wedge I cut out. I can end it anywhere I want, as it can be illustrated with a piece of paper. But once I glue this side to this side, there's no way to move this corner without doing some damage to the side, to the piece of paper. Maybe a little bit more technically related to what I'm going to talk about next, than what I've already talked about. You can think of a disclination, namely this red defect, as made up of a row of dislocations illustrated in these little T's. And that's very much like a charge. You can think of a charge as a row, finite row of dipoles in ordinary electrostatics. So now suppose I wanted to move this, disclination one lattice side over. How do I do that? I need to add a dislocation. But what is a dislocation? It's a whole infinite row of atoms, as you can see here. That I have to add one of these over here. But that's not a local operation. Adding an infinite row of atoms is not going to appear any local Hamiltonian made up of atoms. So that's not allowed. So that's why these disclinations in the actual real crystal are immobile. If you can create one, they can't move. Like if you take a buckyball with 12 disclinations imposed by the topology of a sphere, those disclinations are immobile and are therefore fractonic. Yep.
There, Matt Foster has a question. Matt, if you just want to unmute.
Yeah.
We can't hear you, Matt. I don't know if your sound is on, or I can't hear you at least.
Maybe I can read the question. Let's see.
Yeah, sorry, can you hear me?
Yes, I can hear you. Yeah.
Okay, sorry, I don't know what happened there. So disclinations can be viewed as point sources of curvature and dislocations as like point sources of torsion. So does this have a gravitational formulation, at least this particular version?
There are attempts to do that, but as far as I know, there's no successful formulation of tensor gauge theories on a curved background. so you can think of this as kind of the harmonic version of Einstein gravity, where G mu nu will emerge, but you only expand it around a flat metric to harmonic order. And that's actually, you can think of it as the connection to elasticity. Yeah, but that's a good question. And so people are trying to do that. So now I want to talk about elasticity a little bit more detail. So I'm running out of time, but so imagine a crystal. The crystal is perfect. Then there's a distortion U. Once you have a distortion U, then you want to construct the strain tensor Uij, which is just the deviation of the metric tensor from the flat metric, the preferred flat metric. And in terms of the phonons, it's just a symmetrized tensor like this. It's a di uj plus dj ui. So that's one ingredient. And now suppose I want to, now what's the Hamiltonian? Well, even the classical Hamiltonian has kinetic energy, p squared over 2m. That's the Hamiltonian density. And it has just the u squared, where u is this. Don't worry about indices. This is just some coefficients that are just elastic constants. So think of this as like a bunch of balls and springs formulated in a continuum in terms of the strain tensor. And then topological defects we can formulate in terms of disclinations are non-trivial curls of a gradient of theta. That's a place where when you go around and you enclose the disclination, you're going to get a deficit angle of 2 pi over 6. So it's formulated like this. And a dislocation is when you go around a dislocation point, you will not close a loop. So that's like a topological defect in the displacement field U, in this phonon field U. So U is singular and theta is singular if you have a topological defect. If you don't have a topological defect, then these guys, of course, will be 0. And then there's one more defect. It's a matter of taste if you want to call it topological or not, but it's not just elastic. It's just the creation of an atom or a vacancy in interstitial. So I'm going to call it N sub D is the density of those. It's a difference between vacancy and interstitial. So now I'm going to return to try to make contact between the two subjects. So before I do that, I'm going to remind you or tell you about, if you've never heard about it, about duality, the simplest kind of duality that goes back to the Scoop and Halpern, between bosons and vortices, or equivalently between superfluid, neutral superfluids, and superconductors, or another way to say what a superconductor is a Maxwell Gage theory. So, in a superfluid, you have a fluctuating phase field of the local phase field of the, superfluid, of a boson. But in addition, you have also, those are your Goldstone modes. But in addition, that's the phase field phi. But in addition, and the current is gradient of phi. But in addition, you also have topological defects, which are circulation, non-trivial circulations around some point of this flow. And if you think about what that is you take a curl of this current, but the current is a gradient of phi. So phi has to be singular in order for the curl of the gradient to be non-zero. And indeed, that's the characterization of a vortex. Rho is the vortex density. It tells you all the places where curl of the gradient of J, or circulation of J is non-zero, namely curl of the gradient of phi is non-zero. What's the Hamiltonian? Well, the Hamiltonian is just grad phi squared plus density squared. This is the kinetic energy term. This is just J squared, 1/2 mv squared if you wish. And this is just the repulsion between bosons. And if you're doing a quantum theory, then N and phi are canonically conjugate. On the other hand, all you have to do is rotate these arrows by 90 degrees. Namely, you define electric field, which is perpendicular to J, just as a mathematical object. And all of a sudden, this curl of J becomes divergence of E, and the vortices become the charges. So you've now converted the currents into electric fields, and vortices, vortex density, become the charges of this electrodynamics. And so now, and what happens to the Hamiltonian? Well, this is J, but J is E up to 90-degree rotation. So this is just E squared. And what's the density of particles? It turns out it's just the curl of the vector potential. It's the B. And A and B are canonically conjugate. So this is just electrodynamics. And this is coupled, of course, to the charge degrees of freedom. So if you have a current of these charges, which are vortices, they're the original vortices, they couple to the vector potential like that. Okay, and so that's how electrodynamics or superconductor emerges from the neutral bosons. So how do we connect gauge theory, tensor gauge theory, the fractons to the theory of elasticity? It's exactly this, except add few indices here and there. But philosophically, it's this kind of a connection. It's the duality between an XY model and a superconductor or gauge theory. And so, I could go through this. I don't really want to go through this. I'm just going to highlight some things. You start with a Lagrangian of balls and springs. Here's the kinetic energy, U dot. Here's the elasticity. You formulate the topological defects, which is some kind of a curl of the strain tensor. If the right-hand side is 0, you have no dislocations and disclinations. If the right-hand side is non-zero, you have disclinations or a curl of dislocations. So these are the topological defects. And then if you look at the equation of motion of this theory, it's really just Newton's law. It's simply, as you would expect, as divergence of P, time derivative of P equals to divergence of the stress. This is just a continuity equation for momentum, or you can just think of it as Newton's law. But now amazing thing happens. If I simply reinterpret this equation in the following way, I introduce a magnetic field, which is a 90-degree rotated momentum, an electric tensor field, which is 90-degree rotated sigma j, then this equation just becomes a Faraday law between the magnetic field. So think of this as just the funny magnetic field, dB dt. And when you rotate by 90 degrees, this just becomes a curl of a funny electric field, which has two indices. So this is just a dB dt plus curl of E equals to 0, Faraday law. So Newton's law is just the Faraday's law. And the gauge, and if I want to solve this, or if I want to solve this, how do I solve it in electrodynamics? Well, I simply introduce gauge potential. So then this equation is automatically satisfied. So then I say B is a curl of some funny A, and E is a time derivative of Aij, and a double derivative of some scalar potential. In ordinary electrodynamics, it's just first derivative. It's the gradient of the scalar potential. There's gauge symmetry that appears here. And that's just the fact that this equation or this equation is invariant under these transformations. And everything just appears. This elasticity could just be reformulated in terms of funny electrodynamics. So if you didn't follow that in detail, the only thing you need to know is Newton's law. Here's Newton's law, and realize that there's a stress tensor, and it's the tensor, so you can think of it as a tensor electric field. And momentum is like the vector magnetic field, and so this becomes a Faraday law. And the dislocations become charges and dipoles of this theory. Okay, so here's the dictionary then, just to summarize. And it looks like that's basically what I'll get through, hopefully a little bit more. So here's the Fracton theories formulated in terms of tensor gauge theory, B squared plus E squared. Here's the Gauss's law. Here are the dipoles. So this theory becomes just the pi squared plus U squared, just a bunch of couple harmonic oscillators of this crystal, elasticity of this crystal. That double divergence of the electric field is precisely the topological condition on having a disclination, which is a double derivative or double curl of U, but when I rotate it by 90 degrees, it becomes double divergence. Dislocations are just the pairs of these disclinations, and they're just the dipoles. Phonons become the gauge modes, and so there's a relation here that I've already described. So that's the kind of the very good pausing, stopping point just to pause and to ask you if you have any questions. So this is really the punchline of the talk. Everything else is sort of icing on the cake that I maybe impose on you in another 5 minutes or something like that.
Leo, could I ask a quick question? So
Yeah.
based on this picture, it's clear that you could move a disclination by attaching a dislocation to it. Right? It's sort of hard for me to visualize it on the lattice, but
Sure,
yeah, that I could
okay.
sort of annihilate a charge by bringing a dipole next to it, and effectively it's as if charge has moved. Is that correct?
Exactly, that's correct, yeah.
Okay, so if that's the case, then I ought to be able to move a single fracton. Let's say a fracton sits at the corner of membrane in X cube. I ought to be able to move it if I just brought an external dipole from somewhere and would move, right? But would that not contradict the statement you made earlier that no, you can't actually move a single corner of that membrane, you have to move the other three?
Well, if you have a soup of dislocations around at your disposal, like you have a reservoir of them, then you can move them. And that's in fact how you leave the fracton phase. If I had more time, I would describe it. Condensation of dipoles, of dislocations, is how you become non-fractonic. But that corresponds to melting a crystal.
Gotcha. So just having single dipole is not enough. You need to have a super.
No, you can add one, sure, but then you've moved there only one lattice site. Now what do you do? So you can keep bringing it in. You have to be creating it out of vacuum and adding the energy, core energy dislocation, and bringing it in. Sure.
Gotcha.
But if you want a condensed state of matter, then you need a condensate of those things to be able to, or soup of those to be able to be eaten up as they move, as defects move. Okay, so I'm going to skip through this because there's another formulation called vector gauge theory formulation, which is much more familiar to ordinary electrodynamics, but you have to introduce 3 gauge theories and you couple them together in a very, I might say, beautiful way, where in the way they couple, they end up having still fractonic character, but the actual theories without coupling are ordinary electrodynamics that you're familiar with, but there's this very subtle coupling between these fields, these 3 gauge theories, that gives you fracton behavior of the quasi-particles, of the charges. And so I'm, in fact, fond of this formulation much more, and there's a PRL with Mike Kermely describing all this, and then some considerable elaboration that I will spare you.
So Leo, maybe since you have to run quickly, I know maybe this would be a good, just to make sure we have a chance to have some questions, if you don't mind.
Let me just see what else I have in store for you. Let me just say one more thing, okay? Perhaps. Yeah, let me just say one more thing. Well, maybe two more slides. I think I can get through this. So everything I've talked about so far was about a crystal. But in fact, our experience with crystals, we know in addition to topological defects and phonons and elasticity, we also have vacancy interstitials. So where are one might ask, where are my atoms? Well, of course, I do have atoms. That's the vacancy interstitials. And the way we incorporate them, if they're bosonic atoms, is in terms of this. This is the condensate or mod insulate of these atoms. And we know this because we know from elasticity, quantum elasticity, that we actually have 2 types of crystals. We have a commensurate crystal, or one can say mod insulating crystal, where there are no vacancy interstitials. And we have also incommensurate crystal, which is also known as a supersolid. So there's actually 2 crystals with vacancy interstitials and without vacancy interstitials. So then this immediately tells you, together with the connection to the fracton gauge theories, that there's actually 2 types of fractonic gauge theories. There's one corresponding to this crystal and one corresponding to this crystal. And the amazing thing is, in this crystal, you're not allowed to move the dislocations. Dislocations don't climb. But in this crystal, they are able to climb because you have a condensate of vacancy interstitials, which allow it to climb. And so this is encoded in this equation, a breakdown of this continuity equation that dates back to some work that I did on vortex lattices in 1998 with Christina Marchetti. So if you now turn the crank that I described before, so far, the tensor, the elasticity will become this tensor gauge theory that I described, but the atoms, the bosonic atoms of vacancy interstitials will become a gauge theory that is a conventional gauge theory of E and B. These are the vector gauge theory, and now they're coupled together in a certain way. And so now you predict that there's actually 2 fractonic phases, one where dipoles are completely mobile and the other dipoles have restricted mobility. And you can go between these so we say that this kind of a fracton where the dipoles are not completely mobile are symmetry protected fracton order. And that's what's illustrated here. And if you want to read about details of it, there's a PRL with Michael Pretko dating back to 2018. So with this, let me skip over many things that I could talk about, various phases and phase transitions. So here are the Fracton phases, and you can leave those Fracton phases by condensing dislocations or dipoles. And so you have a quantum phase transition out of that phase. You can think about quantum liquid crystal phases where there's a restricted mobility of topological defects, and they're described by Higgs mechanism of these tensor gauge theories, which is quite interesting. But and one can understand restricted mobility of these topological defects in these layered structures. But let me quit and just flash up this summary and conclusion, which basically says everything that reiterates everything that I've said, but I won't say it. You can just read it. And thank you for your attention, and ask for questions.
Thanks, Leo, for the great talk, and accept my applause on behalf of everybody. So let's ask questions until Leo has to leave to teach a course very soon. But any questions?